In the last class, we had been discussing the property of light when it falls on a metal surface or when it scatters off an electron, and we were led to postulate that light has a dual nature. If you want to explain experiments like interference or diffraction, you invoke the wave nature of light, which is governed by the Maxwell's equations. So, to explain interference or diffraction, you have to think of light as electromagnetic waves, which have wave-like solution. So, this is a particular wave solution, a plane wave solution, which is described by a wave vector k, which is 2 pi divided by the wavelength into n, where n is a unit vector in the direction of propagation of the wave. The wave is also described by the frequency nu, or the angular frequency omega, which is 2 pi times the frequency. So, this is one aspect of the behavior of light. Now, in order to explain effects like the photoelectric effect or the Compton effect, one has to invoke a totally different behavior for light. One has to go for a particle-like description for light, and and the particle is called photon, and one attributes an energy E, which is h cross into omega, where omega is the angular frequency of the wave, and a momentum P, which h cross into k, where k is the wave vector of the wave. So, we see that in order to explain different phenomena, one has to invoke two totally different properties for light, the electromagnetic wave property or a particle property. Now, let us discuss what are the main differences between the wave picture and the particle picture. So, if light is a wave, let us say propagating in this direction n, and this is the mathematical representation of a wave, e to the power k dot r minus omega t, which is the phase, then the main feature which you should note, the main difference from a particle, is that the wave is an extended quantity. That means the electromagnetic wave, the electric field and the magnetic field are non-zero over a region of space. So, the wave is defined over a region of space-time, that is r and t, and it is an extended quantity. So, the electromagnetic wave is something which is defined in this whole region of space, and it varies as a function of time. In this case, we have a plane wave, and the electric field is constant over this whole plane surface over here, and it has a different constant value on a different plane surface. But the point to note is that this is an extended quantity. The electric field is the same, defined everywhere on this plane, and it is defined in this whole region over here, and it varies as a function of time. So, the wave is an extended quantity. Now, what about a particle? A particle, by definition, is something which is just at a given time, the particle has a definite position and momentum. By definition, a particle has at a given time, the particle has a definite position and momentum. So, at any instant of time, it is localized. It is there only at one point in space, and it has a unique velocity or momentum. So, the main difference which you should keep in mind is that a wave is an extended object, is an extended quantity, whereas a particle is a localized quantity. A particle exists only at one point at a given instant of time, whereas a wave is something which is distributed over a region of space. Now, having finished this brief recapitulation of what we had been dealing with in the last class, let us now go ahead to discuss a new situation. Let us discuss an experiment where we have two slits. There is a screen over here, and in this screen we have two slits, slit A and slit B. The rest of the screen is opaque. On this screen, we are shooting some particles from the left hand side. Some particles are incident, a uniform beam of particles is incident from the left hand side. To start with, let us assume that these particles are quite massive particles. They could be something like bullets. So we are shooting bullets uniformly onto the screen from the left hand side. Most of the screen is opaque except for two slits, slit A and slit B. The particles which go through slit A and slit B then fall on this screen over here, and this screen on the right hand side has got detectors which can count the number of bullets as they arrive on this screen over here. So there is some means by which we can count the bullets as they arrive on the target screen on the right hand side. Now let us first consider a simple situation where we have blocked the slit B and only slit A is open. So all the bullets which go through slit B are blocked over here. Only the bullets which go through screen A are allowed to go through and hit the target over here. The target has some counters distributed all over it which will count the number of bullets that arrive, and the distribution of the number of bullets on the target will be something like this. We expect to get the maximum number of bullets at the point which is just behind the opening, and there will be a few stray bullets which will be at a small angle and they will be distributed in some kind of a fashion around the central position. So this red curve over here shows the number of bullets which arrive on the screen on the right hand side and which are measured by the counters which are positioned on the screen on the right hand side. Now let us consider a different situation. Let us consider the situation when screen A is blocked and screen B is open. We expect a very similar pattern except that the center has now shifted to the position corresponding to the slit B, and again we have the maximum in the bullet distribution just behind the slit B, and there will be stray bullets at angles which will be distributed around this point corresponding to B, and they will have some kind of a finite distribution. So this is what happens when either slit A or slit B are opened, and next we ask the question, what happens when both slit A and slit B are opened? So when both slit A and slit B are opened, what we expect is that at any point on the screen, the number of bullets arriving at any point of the screen is equal to the number of bullets that would have arrived if only A were open, which is NA, plus the number of bullets which would have arrived if only B were open. So for most of these parts, the bullets will only come from the slit A. So this is what we expect if only A were open, and for these parts the bullets will only arrive through slit B. So this is what we expect when only B were open. In the intermediate region, there is a finite chance that a bullet may arrive either from A or from B. So the two numbers or the probabilities of the bullet coming through A and B add up, and the number of bullets we get in this region is greater than the number of bullets which you would see if only A were open or only B were open, which you can see by just superposing all of this. So if you superpose all of these curves, you will see that the number of bullets in this region goes up because of the fact that both of these slits are open. Some bullets arrive through this and some bullets arrive through this, and the total number of bullets in this region just increases because of the two different possibilities which are now there. So this is what you would expect if you were to do such an experiment using bullets, and it is quite in keeping with our understanding of classical physics. Now let us consider a slightly different situation where we were to do the same experiment but with some microscopic particles instead of bullets. So let us say that we do the same experiment. We have two slits on a screen, on an opaque screen, and instead of shooting bullets from the left hand side, we were to shoot some kind of microscopic particles, let us say electrons. And on the screen on the right hand side, we had some detector which could count the number of electrons arriving on the screen over here on the right hand side. For example, we could have a TV screen over here, and the intensity of the light on the TV screen would reflect the number of electrons arriving at the TV screen, or we could have some kind of electron counters which could count the number of electron as on different points on the screen on the right hand side. Now, naively, if electrons were to behave just like bullets, just that the mass is different, we would expect a pattern which would be just like what you had if you were doing the experiments with bullets. But for electrons, when you open both the slits, for electrons when you do the experiment with only one slit, when you use only slit B, you get exactly this kind of a pattern, and when you open only slit A, you get exactly this kind of a pattern. But when you open slit A and B together, what is seen is something totally surprising. What is seen is a pattern which looks like this. Now, you may ask the question, what is so surprising about this? Well, the surprising thing is that the number of bullets, number of electrons which arrive at any point on the screen when both the slits are open, that is, the total number of electrons which arrive at any point on the screen when both the slits are open, let us say A, B, should be greater than or equal to NA plus NB. There is no way it can be less. That is, when Na is the number of electrons which arrive over here when only A is open, Nb is the number of electrons which arrive over here when only B is open. We expect when both are open, the number of electrons that arrive over here should be at least equal to the sum of the number of electrons that arrive when only A is open and the number of electrons that arrive when only B is open. But what is observed is that the number of electrons actually goes down in certain points on this screen, which is something very hard to explain if you were to interpret the electrons as either coming through this or through this, because in that situation this should be just equal to Na plus Nb. An electron coming from this side could either go through this and come to a point over here, or it could go through this and come to a point over here. So, the number which arrives when both the slits are open should be equal to the sum of the numbers which arrive when they are open individually. What is observed is that at certain points on the screen, the number of electrons arriving is actually less than Na plus Nb, and there are certain points where actually no electrons arrive. So, you cannot interpret, you cannot explain this, you cannot add up two positive numbers and get something which is less than the individual numbers themselves. It is not possible. So, you have to abandon this kind of an explanation for the motion of the electron and how it arrives at the screen. So, the question is, how does one go about explaining this phenomena where the number of electrons arriving on the screen over here actually goes down when both the slits are opened, whereas one would expect it to go up when both the slits were opened? Well, the solution to this problem is as follows. In order to explain this phenomena, one has to invoke the fact, one has to postulate that the electrons actually behave as waves. So, now the explanation is not very difficult to provide. The incident beam of electrons over here is a wave. Let us denote that wave as psi naught. So, the incident beam of electron is actually a wave. The wave arrives on this screen over here. When the wave encounters this opaque screen with two slits A and B, there are secondary waves which are emitted from the slits A and the slit B. So let the secondary wave emitted from the slit A be psi A, and the secondary wave emitted from the slit B be psi B. These two waves propagate individually, and they pick up they have to propagate through different paths to reach any given point on the screen over here. As a consequence, they pick up different phases when they arrive on the screen over here. The resulting wave over here is the superposition of these two secondary waves, psi A plus psi B. So what we have is that the wave representing the electron is the superposition of these two waves over here. So let us briefly look at what happens. So we have on the screen on the right hand side where we have the electron counters, we have a wave psi, which is the superposition of these two secondary waves, psi A and psi B, which are emitted from the two slits A and B. Now the wave psi A and the wave psi B are the same wave before they entered the slit. So we have psi 0 and psi 0 for both of them, but they pick up different phases. So the phase for A, let it be e to the power theta A, and the phase for B we denoted by theta B. So these two waves pick up different phases as they propagate through different distances, and these two phases could add up constructively or destructively. So this is the phenomena of interference. So depending on the position on the screen on the right hand side, these two waves could add up either constructively or destructively, and when they add up constructively, the function psi over here is the sum is greater than these individual parts, but when this adds up destructively, the psi over here is actually less than these individual parts. And we have to now interpret the psi in terms of the number of electrons hitting the screen on the right hand side, and this is done by saying that the probability of the electron so the probability of finding an electron on any point on the screen over here, which is what is shown over here, dpx, this is the probability of finding the electron in the interval dx on the screen on the right hand side, is the mod square of this wave, which is called the wave function. It is the mod square of this into the interval dx. So this can explain the phenomena which we see where the number of electron actually goes down, because the secondary wave emitted from A and the secondary wave emitted from B, they pick up different phases. When they come to the screen, you could have either constructive or destructive interference, and since the probability of finding an electron is given by the mod square of this wave function, the total number, the probability could either increase, the probability could be greater than psi naught square. So psi naught square is the probability which you would expect if there were no interference and only one slit were open, but when both are open, the resulting probability could be either more than this or it could be less than this, depending on the phase at which the electrons arrive, depending on the relative phase between the two secondary waves. So we see that we have to invoke the wave property for the electron, which is something totally new. In our classical understanding of the electron was treated as a particle. So this is the classical picture of the electron. The classical picture of the electron is that it is a particle, and for an electron we believe that at a given time we have a definite position and we can define a definite momentum. But we see that in order to explain this kind of an experiment, the two-slit experiment, where you have an electron beam incident on two slits, we have to abandon this kind of a picture and we have to invoke a wave picture of the electron. So, the electron is described by a wave. This is the picture that we have to invoke if we want to explain the two-slit experiment. Not only that, the electron is described by a wave, but we have to also give it the property that we can superpose two such waves and get another wave which describes the electron, the behavior of the electron. This is what is called the superposition principle. So, in this situation, when only one slit is open, when only slit A is open, there is one secondary wave coming out from the slit A, which describes the behavior of the electron when only one slit is open. Similarly, when only slit B is open, we have a secondary wave coming out of slit B, and this describes the situation when only once this slit B is open. But in a situation when both of these are open, we have to find out the resultant by superposing these two waves, and this is another property which we have to attribute to the electron or to this whole kind of mechanics. So, the first property which we have to attribute is that the electron is described by a wave. The second property is that we can superpose such waves, and these again describe the behavior of the electron. Now, the wave picture for the electron introduces something which is drastically new. What are these new consequences of the wave picture? The first new consequence is that a wave is an extended quantity. So, when you talk of the electron as a wave, the wave is defined in a whole region of space. So, it is as if the electron were distributed in this whole region of space. You cannot ask the question, where is the electron? It is distributed in this whole region of space. So, in the situation which we have been dealing with over here, before the electron is incident on the screen over here, the electron, a single electron, is distributed over this whole region over here, and after it passes through this, the single electron is again distributed in these two secondary waves, and it is something which is quite different from our original particle picture, where the electron at any given instant of time had a definite position and momentum. Now, the electron is something which is not there at one point, but it is distributed in this whole region of space. This is the first drastic new thing which the wave picture brings about. But then you may ask the question, since the electron, there is only one electron and it is distributed in the whole region of space, if we make a measurement, do we get a fraction of the electron at some point? Suppose I were to simultaneously make two measurements at two different points, and I were to try and determine, is the electron at these two positions. Is it possible that I find that half the electron is here and half the electron is over here? Well, this may seem plausible because the electron is actually, in a wave picture, the electron is distributed over the whole region of space. But experiments reveal that we never, even though the electron, when you describe it as a wave, even though the electron is actually distributed over a region of space, when you make a measurement, you never find a fraction of an electron at one point and a fraction of the electron at another point. Whenever you make a measurement, you always find that there is the one electron at some position. So, the interpretation of the wave is something quite subtle. The wave has to be interpreted as giving the probability of finding the electron at some position. So, the modulus square of the wave. So, we have a wave psi which is defined at over an extended region of space, and it could be a function of time, and this represents the electron, and it is defined over a region of space. The mod square of this, the modulus square of the wave function, gives us the probability of finding the electron at some position, and the probability is a fractional number, but we never find the fraction of an electron at one point and another fraction of it at a different position. When you make a measurement, you always either find one electron or you get nothing. So, the electron somehow although it is an extended thing represented by a wave, whenever you make a measurement, it somehow manages to materialize again as a particle at a definite point, at a definite position. So a measurement always reveals one electron at one point. So whenever you make a measurement, it behaves like a particle. But when it propagates, you have to invoke wave properties to describe the electron. So this is something quite mysterious, how suddenly sometimes it is a wave and sometimes it is a particle. But again we see that this is nothing but the dual nature which we had encountered when discussing light also. So we see that even massive particles, even things like electrons, have to have a dual nature. They have to be described both as a wave as well as a particle. So this is the first interesting thing. Let us now discuss another very interesting aspect of this experiment. In this experiment, we have electrons coming from the right hand side, which, as I have told you, we have to think of as a wave incident from the right hand side. The electrons go through slit A and B, and then we see them on the screen over here. Now suppose I ask the question, through which slit did the electron pass? Let us for a few minutes just go back to the situation where we had bullets. If we shoot bullets from the right hand side, we can definitely say whether a particular bullet actually went through slit A and then hit the screen, or it went through slit B and then hit the screen. There is no ambiguity about this, and given any point on the screen, there is a finite probability that the bullet may come through A and reach that point, or there is a probability that the bullet may come through B and reach that point. Can we ask the same question for electrons? This is the next question we shall address. So suppose I were to put two detectors over here at A and B, which would tell me that if detector A clicked, it would tell me that the electron has gone through A and then arrived at the screen over here. So I would first see a click over here, and then I would see a spot over here, the electron indicating that the electron has come through the slit A, or I would see a click in the detector B, in the detector located at slit B, and then see a spot over here which would indicate that the electron has actually gone in through slit B. And this, but okay, it is observed that if you do such an experiment, if you put detectors over here and then try to see what happens on the screen, it is found that the moment you put detectors over here and here to record if the electron either went in through A or through B, you no longer get the interference pattern on the screen over here. You get back the predictions of the classical picture. So what happens when you put a detector, even if you use electrons, but you put some kind of a device here and here which will find out if the electron went through this or through this, the moment you do this, you lose the interference pattern which occurs over here. And what you find is that you will get a pattern which is very similar to what you would get with bullets. So once you put detectors over here and you can determine whether the electron actually went through this or through this, the results also correspond to a situation where the electron does go through this or go through this. So but if you do not make such a measurement, if you do not make a measurement to find out whether the electron went through this or through this, what you get is something quite different. You get an interference pattern where their number of electrons arriving actually goes down at some points and it goes up at some points. So what do we see? We see that if you actually try to determine which of these two paths, which of these two possibilities the electron adopted, if you actually try to determine which of these two choices the electron made, if you try to determine if it went through slit A and then arrived here or through B and then arrived here, the mere act of measurement does not allow this kind of an interference to occur, and what you get is the superposition of the two classical pictures. That is the number of electrons which would arrive if they went through A and which would arrive if they went through B just get added up. But if you were to not make this intermediate measurement, if you were to not try and determine through which slit the electron went, then these two possibilities, they actually interfere. So the secondary wave corresponding to the electron going through here and here then interfere, and we get an interference pattern on this screen over here. So this is an interesting thing which we don't experience in classical mechanics. The first thing is that the act of measurement changes the outcome of the experiments. This is something totally new which we don't have in classical mechanics. In classical mechanics, for a particle in motion, in principle you are free to measure its position and momentum as frequently as you like without making any change at all in the outcome. But we see that when once you go to the microscopic world, the fact that you have made a measurement changes the outcome of the experiment. The second feature which you see is that whenever you have two alternatives which the particle coming from here could take, then the waves corresponding to these two possibilities, these two alternatives, they interfere and they give rise to an interference phenomena, which is something totally new and unexpected in classical mechanics. So in the next lecture, we shall go on to a more detailed mathematical description of these waves which correspond to particles. For today, let me stop over here.